I'd like to start with the last topic from the yesterday's lecture. Let's briefly discuss about this special case, and then we will have an exercise which is gonna be somehow related to the multiple regression and also to this topic when X is binary. This is quite popular case when regressor, when X is represented as a binary variable. So what does this mean, binary variable, and how the interpretation and all the mechanics of our steps changes. So far we used continuous variables as regressors, right? So we had, for example, the class size, which takes any number from something like 15 to 25, right? In that data set, we had percentage of English learning students, which is also from 0 to 100, any number. But sometimes we can use binary variables as regressors. And these binary variables, the variables that are taken only two values, 0 and 1. So you are familiar to these variables from our statistics courses, because there we use these variables to group the whole sample into two parts, like, for example, by gender, females and males. Or we also used the location, like urban or rural region. So you remember we did some empirical exercise on statistics when we tried to compare, I guess, the rural and urban districts in Irkutsk Oblast, and then we compared some numerical characteristics. I don't remember exactly what was that, but this is another way how we can use this binary variable. Or, for example, if we are talking about our case about class sizes, we can mark on one, like small classes with 1 and large classes with 0, something like this. And also, regarding the terminology, this binary variable can be called sometimes indicator variable, or sometimes maybe it is more popular name dummy variable. So don't be confused whenever you hear something like dummy variable, binary variable, or indicator variable, that's the same. We are talking about the same thing. Let's see an example how this works, and you will see some familiar things here. Let's define a dummy variable or binary variable di such that it equals 1 if the student to teacher ratio in district is less than 20, and it equals 0 if the student to teacher ratio is greater than or equal to 20. So we kind of divide all districts into two groups. One group with small classes, and this group will be marked with 1, and another group is districts with large classes, and we mark this group with 0. So then a regression with a single binary regressor will look like this. So we have beta 0 plus beta 1 di plus the error term. Now the problem is with the interpretation, because since d is not continuous, there is no line, right? So we are not able to draw a line because d is only 0 or 1. There are 2 points on the x-axis. And we cannot call beta 1 a slope of a line because it is not a slope anymore. So there is no line, and definitely we cannot think about beta 1 as the slope. So we just call this the coefficient on d1. Like, well, it's not a big error or mistake if you call it slope, but it's not kind of technically, it's not a slope. It's just a coefficient. What does this mean? If you remember, beta 1 was a change in y when x is changed by 1 unit. Now, what beta 1 means if we are talking about the binary regressor? Let's simply write down two expressions when d is 0, and in this case the expected value of y given given d equals 0 is this. So we just plug 0 in the place of this expression and we have beta 0. Well, technically I'm not fully precise with this formula. I must write the conditional expectation, right? It must be conditional expected y given d equals 0. It's not an unconditional expectation, but please forgive me for this small impreciseness. So if d is 1 and a district has large classes, then we plug 1 on the place of d and we have the expectation of y for large classes being beta 0 plus beta 1. So what do we have in this case and what do we have in this case? Can anybody help me? Does anybody remember from statistics what is this and what is this? So we have two groups. One group of districts with small classes, one group of districts with large classes. We have expectation of a test score for districts with small classes. We have expectation for districts with large classes. What do we have? What does this look like? Any ideas?
Like an experiment.
Well, technically it's something like an experiment, yes. I mean, we have two means, mean for one group and mean for the other group, conditional mean for one group, like treated group, and the control group. And then what we did when we used this distinction? When we wanted to compare two population means, right? So we had two groups. We estimated population means for one group and for the other group, and then we wanted to compare them with the help of t-test. So the same thing is applicable here. Exactly. When beta 0 is the population mean when d is 1, when d is 0, sorry, this is just mu for this group, like mu1, for example. And this is the population mean when d is 1. So it's mu2. Right? So the difference between mu1 and mu2 is beta 1. So this is the difference between two population means. And this is exactly related to that topic of the t-test from statistics. So the OLS estimator, again, we don't know what is beta 1, what is beta 0. They are unobserved, and we need to estimate them. But once we estimate beta 0 and beta 1 with the help of OLS, what we will get? We will get beta 1 hat, and this is going to be the difference between sample averages. So there is going to be sample average for the first group, beta 0 hat. There is going to be sample average for the second group, which is going to be beta 0 hat plus beta 1 hat. And beta 1 hat is going to be the difference between two sample averages. Now, how can we test that two groups are different in their population means? Either with the help of t-test from statistics, or we know the simpler way. We know how to test whether beta 1 is significant. We just need to look at the t-value of beta 1 hat. And the two results will coincide. So the regression with a binary variable is fully equivalent to performing a test of the difference in means. Two methods are just copying each other. And after this, we will see this on the real data. So we will compare the two results. So, and here is an example for our test score case. When we regress the test score on this binary variable or dummy variable, which we defined as 1 if class size is less than 20 and 0 if it's larger, and we estimate the model like this. So these are two estimated coefficients, beta 0, beta 1. So what does this mean? It means that the sample average of a test score when d is 1 equals to the sum of these two numbers, right? And the sample average when d is 0 is 649.98. Only this part. So the difference between these two sample averages is 737. So basically the districts with the larger classes on average have 737 points less in the test score. Well, we know how to test a single coefficient, significance of a single coefficient. We just need to calculate t-value. So t-value is calculated simply by dividing the coefficient by the standard error sign parentheses. It's 4,043. And we know that as a rule of thumb, we need to compare this with 196. Again, we don't need to explicitly compute the critical value. As a rule of thumb, you can remember that if we test the hypothesis on a 5% significance level, then the critical value is going to be 196. If the number of degrees of freedom is very small, if your sample is like 10 or maybe 5, then yes, then the critical value is going to be much larger. But in this case, we have 420 observations, so the critical value is going to be like 196, and then some like small numbers afterwards. So we see still that this is much larger than the critical value. So this difference is statistically significant, and the districts with smaller classes tend to have larger grades on average. And this is fully equivalent to the t-test. Yeah. So that's what I was going to tell you yesterday regarding this special case of binary variables. So with the help of this special case, we can replicate the result of t-test. And as you see, it is much easier because in t-test we need to proceed many different steps, like counting the sample averages, sample standard deviations, then performing f-test, whether variances are equal or not equal. In this case, by the way, we assume that variances are equal because we do not have this distinction, right? And then finally we arrive to the result. In this case, it's a bit faster. Any questions?
No, I have no questions. Yes.
Okay, so then I will also upload this to the YouTube as the additional part to the lecture.